Welcome, everyone. We're going to be looking at an introduction to energy in this section. Energy is the ability to do work. And if you remember from physical science, work is equal to force times distance. Now, you may recall that there are many different forms of energy. Two of the main ones we talk about are kinetic and potential, but you've also heard of radiant energy, which is energy from the sun or light energy, and other forms of energy such as chemical energy, electrical energy, nuclear energy, and so on. We're going to focus on kinetic and potential for the moment. You see, kinetic energy has to do with motion. We've talked about how matter has kinetic energy. The difference is that, for instance, the solid state has very little kinetic energy, whereas the gases have a lot of kinetic energy. It all has to do with the amount of movement. But then you also have potential energy, which has a two-part definition. Potential energy can be called energy due to position or stored energy. In some textbooks, you'll see that they divide this. For instance, chemical potential energy would be a form of potential energy where the energy is stored. For instance, gasoline has chemical potential energy. A battery, the food we eat, the coal that we use to burn to create electricity. Those molecules, there is energy stored in them, so they have potential energy. But it can also be due to position. For instance, you may have heard of the example of a boulder on top of a hill. The position of that boulder has the potential to do work. Or perhaps water behind a dam. If you allow the water to flow, that water, that movement can be used as a source of energy. Which also brings me to this point. Energy can be transferred from one form to another. So you can convert potential energy into kinetic and vice versa. So as you can see, there are different forms of energy. Now, measuring energy, there's several units. Now, the official SI unit of energy is the joule. It is a derived unit. However, a very common non-SI unit of energy is called the calorie, which is abbreviated with CAL. By definition, the calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, if you look below here, there are several conversions. One of them here is, the conversion to go from calories to joules is 1 calorie is 4.184 joules. And if you recall, the prefix kilo means 1,000. So if you have 1,000 calories, that's equal to 1 kilocalorie, or 1,000 joules is equal to 1 kilojoule. However, there's one important one I want to look at. When we measure the amount of energy stored in food, we use a calorie with a capital C. Now, the nutritional calorie, which is with a capital C, is actually a kilocalorie. In other words, a calorie with a capital C is actually equal to 1,000 calories with a lowercase c, which would be the same as what we call a kilocalorie. So if you look, a calorie with a capital C is essentially a kilocalorie, which is 1,000 calories with a little c. So I hope that doesn't confuse you, but calories with a capital C are only used in food labels. So for instance, if your caloric intake was, let's say you can eat 3,500 calories a day, that would be 3,500 calories with a big C, not with a little c. Anything that has to do with food, it's actually measured in kilocalories or calories with a big C. And then we have one more here called the kilowatt hour, and that's equal to 3.6 times 10 to the 6 joules. So here's a table from the textbook with the some of the mainly used conversion factors. And with this, we can do two quick practice problems using these conversion factors. So in this first one, we want to convert 1,750 calories to joules. Now notice the calorie is with a capital C. So let's use dimensional analysis to solve this problem. So one of the things you could do right off the bat is to convert calories with a big C to calories with a little c. You see, a calorie with a big C is actually 1,000 calories with a little c, and that will allow you to cancel. So when you do the math there, you're actually, when you multiply by 1,000, you're going to have, right now it's going to become a very big number. It's going to be 175,000. Now, if you want to do this in one step, because we do want to go to joules, then the next conversion is we want to get rid of the word calorie. So 1 calorie has 4.184 joules. And what you would do now is you would then multiply by 4.184. And what we're going to do here, let me write the entire number. We get 7322000. And that would now be in joules. If we want to round this, we would round this to 3 significant figures. So I would use scientific notation for this. And if I want to show 3, I would go with 7.32 times 10. And if you look here, there's a 0 way out here. So you got 1, 2, 3, 4, 5, 6 times 10 to the 6. And this would be in joules. That would be the answer with 3 significant figures. Now, we have a second problem. So that was number 1. Number 2 is we got 235,000 calories. Now, notice this is with a little c, and we want to go to kilowatt hours. So based on the conversion factors that we saw earlier, we probably want to go to joules first, and then from joules to kilowatt hours, we would use this conversion factor here. So to go from calories to joules, we want to go here just like we did previously. 1 calorie has 4.184 joules. And again, set it up so that the calories cancel. And what you're going to end up doing here, you're going to end up dividing. So we're going to divide by 4.184. And if you want, we could do this in one step. Because I know you're going to get 56166 on your calculator with a decimal. But then what we could do is we can set this up using the other conversion factor down here. Notice a kilowatt hour has 3.60 times 10 to the 6 joules. So we want to go to 1 kilowatt hour, and it's 3.60 times 10 to the 6 joules, just like this. So there's a 6 here, allowing the joules to cancel. So when you multiply the two numerators, the 235,000 times 4.184, and then you're going to divide by 3.6 times 10 to the 6, the answer that we're going to get, we're going to round it. Well, I got this here, and I'm going to round it now to significant figures. Got this very long answer here. All right, so in the next slide here that we have the law of conservation of energy. And what happens here is the law of conservation of energy basically says that energy is not created nor destroyed. As I mentioned earlier, energy is transformed from one form to the other. We talked about how kinetic energy can be converted to potential and vice versa. For instance, water behind a dam is potential energy, but once that water starts to flow, the potential energy starts to get converted to potential energy. Now we're going to look here at heat. Heat is energy that is transferred from a body or a substance that has a higher temperature to one at a lower temperature. You see, heat always transfers from the hotter object to the cooler object, not the reverse. On the bottom here, we want to explain using this way that heat is explained, the way it's transferred. We want to explain in part A, when you burn your hand on a hot frying pan, explain how heat is transferred. So think about that for a moment. So when you burn your hand on a hot frying pan, the reason your hand feels hot is because the frying pan has a higher temperature, and heat always flows from higher temperature to lower temperature. So the flow of heat goes from the frying pan to your hand, and that is why your hand feels hot. In the second example, it says that your tongue gets cold when you eat ice cream. So let's think about that for a moment. Now, the reason your tongue gets cold, and I'm going to give you the correct and then the misconception, is because when you are licking ice cream, your tongue is losing heat. Your tongue is the object with the hotter temperature, and it's being transferred to the ice cream, which has the lower temperature. So the reason you feel cold is because you are losing heat. The misconception is that people think that your tongue feels cold because coldness is transferred from the ice cream to your tongue, and that's not true. Whenever you feel cold, it's not because coldness is transferring towards you, it's because you are losing heat. So imagine you're holding on to an ice cube. Your hand feels cold because your hand is losing heat to the ice cube. Eventually the ice cube starts to melt because it's receiving the heat. So that's the formal explanation of how heat is always transferred from the hotter object to the cooler object. Now, we're going to talk about what is endo and exothermic change. Endothermic, basically, it could be a physical or a chemical change, but endothermic is it requires heat, okay, or energy for it to occur. Now, the first example is a physical change. Notice that heat is going from, is being applied here. Notice that whenever it's an endothermic reaction, the word heat is written on the reactant side. When it's exothermic, which you'll see in the next example, heat is written on the product side. So if it acquires heat, you'll see that water as a liquid, by absorbing heat, it's going to, in this case, it'll boil, which is a physical change, and it will become a gas. So that would be an example of an endothermic change that has to do with a physical change. As far as an exothermic change, it can also be physical or a chemical change. And the example that I have here is water when it condenses, which is the opposite of boiling. Water, when it's a gas, if it releases heat, it will cool down and become a liquid, and there's the heat that was released. So you see the word heat placed on the product side. But it doesn't always have to be a physical change. It can be a chemical change. The electrolysis of water is an example. In order for water to break apart, it actually requires electricity, electrical energy. So notice how the electrical energy is also placed on the reactant side. It needs it. So when water receives this electrical energy, a chemical change takes place that will split the water into hydrogen and oxygen gas. Since you're making two new substances, this is a chemical change. Another example is hydrogen burning. In fact, for the most part, any chemical reaction undergoing combustion, which pretty much means that something is burning, oxygen is one of the reactants in the equation. When a hydrogen burns, what's going to happen is, or any other combustion, you're going to form a product. In this case, we're forming water vapor, but heat will be released. And when heat is released, you will feel, if, for instance, if this took place in a test tube, the test tube will feel hot. If an endothermic reaction took place in a test tube, you'll see that the test tube actually will feel cold versus hot. So when heat is released, as in an exothermic reaction, it will get hot. And if heat is absorbed, which is what happens in an endothermic reaction, the test tube will feel cold. So here is a little summary. Notice that in physical changes, it says that if the reactants have greater kinetic energy than the products, it's an exothermic process. I'll show you a graph to explain that. And it says if the products have a greater kinetic energy than the reactants, it's endothermic. And I will show you that. The one I did mention was for chemical changes. Notice that if a chemical change occurs, if the surroundings get hotter, for instance, the test tube feels hot, that's because heat was released. And whenever heat is released, that's exothermic. If the test tube feels colder, and that's the result of heat being absorbed, then that's an endothermic reaction. So Exothermic is a process in which heat flows out of the system and into the surroundings. Heat is going outside, it's exiting. And then endothermic, endo means going in. That would be a process in which heat is flowing from the surroundings into the system. When we say the system, that could be a beaker, a test tube, wherever the reaction is taking place. Now, I am going to show you this process through a graph. If you look here, notice on the left we have an endothermic reaction. The reactants, and this is, I'm going to show you as we see this, I'll draw it a little differently. You start from left to right, and you start off as a reactant, you overcome this hill, and then notice you start off as a reactant, and you end up as a product. If you end up higher than where you started from, okay, and we call this difference from the start to the end, that difference is known as delta H, which is known as, it's called change in enthalpy, okay, change in enthalpy. Notice that, let's say this was 0, and this was, up here would be a positive number. Let's say it was 20. So the change here would be positive. Delta H would be a positive number. So if the enthalpy is a positive value, that means that the products are higher than the reactants. So what that indicates is that that amount of heat needed to be absorbed. In other words, when enthalpy is positive, which we represented as delta H, that represents an endothermic reaction. Now, conversely, we have an exothermic reaction, okay, and the graph doesn't show it. I'm going to draw it kind of like the one I did on the left here. You're still starting over here. You overcome this hill, and then notice how you end up lower than where you started. You know what I'm going to do? Let me make this a little bit more drastic so you can visualize it better. So you started here. These are the reactants. This is the product. And you ended lower than where you started. So this difference from where you started to where you ended is still called delta H, but now you ended up lower than when you started. In this example, as you can see in the examples, the delta H is going to be negative. When delta H is negative, that is indicative that it's an exothermic reaction. That means that heat was released. Now, in the future, you're going to learn about this, but this hill that we have to overcome, which is this distance from here to here, and I'll draw it over here as well, okay, the distance from where you start to the top of the hill, we call that the activation energy. I'll write it over here. And activation energy, I'm going to give you a quick definition, is the energy needed to get a reaction going. Every reaction requires a certain amount of energy so that the reaction can take place, and that is called the activation energy. Some reactions have very high activation energy, some have very low. The higher the hill, the more the activation energy, the slower the reaction will take place. Fast reactions usually have very low hills, or they have very low activation energies. So going back, if you see in the endothermic, notice how the products are higher than the reactants. So if you go back here, notice when we said it was endothermic, you see the products are higher than the reactants, and that's represented by that graph. Now, look at the exothermic over here. Notice that the products are lower than the reactants, so we'll go back and verify that. In an exothermic, notice that the reactants, okay, have a greater kinetic energy than the products. In other words, the product is lower, and you can see that over here. So that's what I was trying to tell you earlier using these two graphs. And here you have a summary, okay? This doesn't show you the whole picture, but here, this first one is the exothermic. So you're starting over here, and you go through your reaction, and you end up lower, okay? And again, that difference from where you started to where you ended right over here, that difference is called delta H. So in an exothermic reaction, energy ends up being released. And then this second one down here, you're starting over here, but you end up higher than when you started. Again, that difference over here is still called delta H. The difference is that on an exothermic reaction, it's negative because you end lower, whereas in a endothermic, it's positive because you end up higher than where you started. So the reason for that is because in an endothermic reaction, energy is being absorbed. So I wanted to go ahead and explain those two graphs. Now, the last thing I'm going to tell you, this will help you for an assignment, is these are physical changes. Okay, so remember that we talked about you got a solid over here, you got your liquid and your gas, and any process, for instance, if you're going from a solid to a liquid, okay, or from a liquid to a gas, if you recall, from a solid to a liquid, okay, we mentioned that that's going to be melting, okay, and from a liquid to a gas, we had a few names for this. The general one is called vaporization. We had mentioned that. But a liquid to a gas can also be boiling. We'll put boiling. Let me fix that over here. We'll call it boiling. And we could even use the word evaporation, because evaporation, you are going from a liquid to a gas. So I'll put that there. And we did mention that you can go from a solid straight to a gas, and that's through sublimation. Now, whether it's vaporization, boiling, evaporation, sublimation, or melting, any process in which you're going from a solid to a liquid or to a gas, it requires energy. So what I'm going to do here is I'm going to put here that any process, when you're going in this direction, the arrow that you see at the bottom, since it requires an input of energy, it's an endothermic process. And if you look at the opposite to this, if you're going from a liquid to a solid, we know that's freezing. And then we have from a gas, we mentioned this earlier, condensation is going from a gas to a liquid. Water is given off, or not water, heat is given off, and it starts to liquefy. And we also learned that you can go directly from a gas to a solid, which is called deposition. So any process in which you're going in the opposite direction, as I did on the bottom, in order to go from a gas to a liquid or from a liquid to a solid, you're releasing energy. So those processes would be exothermic. So these are all physical changes, but you could see that I divided the top part. You're going from a gas towards a liquid or towards a solid. Those are exothermic processes releasing energy or heat. And in the bottom half of the picture here, you have processes going from either a solid to a liquid, or a liquid to a gas, or from a solid to a gas directly. And that requires an input of energy, and that's what makes it endothermic. So with that being said, using that chart I just made for you, circle all the following changes that are endothermic. So freezing, okay, freezing, if you look up here, in freezing, you are actually releasing heat. So the question was to circle the ones that are endothermic that require heat. So freezing is out of the question. Vaporizing. Well, vaporizing, if you look down here, vaporization, there is an input of energy to go from a liquid to a gas. So we're going to go ahead and let me use a different color here. We're going to circle vaporizing. Now let's go back. Sublimation. Sublimation would also be an endothermic process, because if you look down here, you're going from a solid to a gas, so there's an input of heat or energy there. So we're going to circle sublimation. Now melting, if you look at melting, melting is also on the bottom half here. So we had three of them here. These are the ones that we we're going to circle on the other page. In order for a solid to melt, there's an input of heat, okay? And then we got deposition, but deposition is the opposite of sublimation. That one actually releases heat when a gas goes straight to a solid, such as in hail. That would be an example of deposition. So we're not going to circle these two. Those two are exothermic processes. And then in the final example, when a student mixes hydrochloric acid and sodium hydroxide in a test tube, it says the test tube feels hot. This is a key word right here. Test tube feels hot. So is the reaction endo or exothermic? Now, here we're talking about a chemical reaction. So if you have a test tube and the test tube feels hot, what we said earlier is that when something is exothermic, the reaction is releasing heat, so the test tube will feel hot. And that's going to be the explanation. Had the test tube felt cold, okay, then it would have been endothermic. But in this scenario, the test tube feels hot because in the chemical reaction, heat is being released, and the release of that heat causes the temperature of the test tube to go up, therefore it feeling hot. One last thing I'm going to mention, this is how, for instance, ice packs and heat packs work. Let's say an ice pack is actually endothermic. So when you have an instant ice pack, you're told to kind of like squeeze the ice pack, and what you're doing is you're breaking a seal, you're activating it, causing the chemicals inside to react. Now, the reaction is endothermic, so what's happening is those chemicals are absorbing energy from the surroundings. As energy is being removed from the surroundings, which is the remainder of the pack, okay, which is the ice pack, the temperature starts to go down because heat is being absorbed. It's being removed. So as the chemicals react, heat is being removed, so the ice pack starts to get really, really cold, and that's how it takes into effect. A heat pack would be the opposite. When you activate a heat pack, the chemicals start to react, but this time those chemicals, when they react, they release heat, and by releasing heat, they cause the temperature of the ice pack, or of the pack here, to go up, and it acts as a heat pack versus an ice pack. So that is one way in which, chemicals are used. The reaction of those chemicals, whether endo or an exothermic, can create either the release of heat, which would be used for a heat pack, or an endothermic reaction would absorb heat, causing the surroundings to get cold and thus producing an instant ice pack. Okay, so I hope that information is also helpful to you.